Okay, moving on to the next section, coordinates and distance. It's all a bit dull, but we do all need to make sure we're doing the same thing. So again, back to our Beamer file, Control L. So for the whole of this course we're going to be dealing with problems in the plane, for which I'm assuming that I have a horizontal x-axis, a vertical y-axis, and a point of intersection called the origin. Typically one calls the x-coordinate of any point P, which is described by the shortest distance from P to the y-axis, as the x-coordinate, which is the abscissa, and the shortest distance in the vertical direction from P to the x-axis, the length PM, the y-coordinate, is called the ordinate. Again, you can access shockwave files and GeoGebra files associated with that figure. So this is all described here. Now, having done that, we can talk about the distances between any 2 points in the plane. So, whilst one can use just general letters for points in the plane, it's very helpful if you use suffix or subscript to denote the x and y coordinates of points. So here I've got a point P called P1. A point P, but I've called it P2, and the coordinates of P1 are x1, y1, and the coordinates of P2 are x2, y2. It's very simple to determine the distance between P1 and P2 by drawing a right angled triangle, as I have here, and use Pythagoras' theorem. The length of the base and the length of the adjacent side, the opposite side here, so the height and the hypotenuse satisfy Pythagoras' theorem, and this length here is clearly the difference between x2 and x1, and this height here is clearly the difference between y2 and y1. So this squared is that squared plus that squared, which is just indicated by this expression here. So for any problem, the distance between 2 points can be written as the square root of the sum of the squares of the difference of the x coordinates of the 2 points and the y coordinates of the 2 points. Now, in particular, if one of the points is the origin, as we have here, then clearly the x1 coordinate is 0, the y1 coordinate is 0, and if we label the x2 coordinate just as x, the y coordinate y2 just as y, then that same formula with zeros in for x1 and y1 just gives me this. And again, that's very obvious from Pythagoras' theorem that OP squared is equal to x squared plus y squared. Now, in general, we're going to be talking about points P with coordinates x, y that could lie anywhere in the plane. And typically, we're going to state a rule about that particular point. Say it's equidistant from a particular point or from a particular line, or a series of other descriptions. So for example, if we prescribe that P has to satisfy where the case where x and y are both positive, of course P lies in the upper right hand quadrant. If on the other hand x is equal to 0, then that's clearly the y-axis, or if y is equal to 0, that's the x-axis. But we might have a different rule. For example, we could say that P was always a fixed distance, a distance of 2 from a particular point, say 3, 1. Well, that clearly gives a circle, and what we're interested in doing is describing mathematically the equation for that circle using the coordinates x, y of a general point P. And it turns out that you get this. And this is a type of problem that we will look at very simply at the outset. This is called the equation of the locus of P. As I've said, it's clearly a circle, centre 3, 1, radius 2. Now, there are two types of problems that we will typically be looking at. One is much easier than the other. Typically, we're told a geometrical fact, some rule, from which we can determine the equation of a locus. What's more difficult, and is what usually arises out of solving some different problem, is a locus appears, some equation, and one wants to be able to identify what that is, whether it's a circle or a straight line or whatever other shape. And the only way one can do that is to become familiar with a series of different standard shapes. And so the primary part of this course is to be able to identify standard loci, and then we'll also look at a series of interesting problems and also properties of those loci. So as I've said here, the converse is more difficult. If you're given the equation, what does it represent? So we'll start off by looking at the straight line, which is the most basic of the problems we will look at, but it's still necessary for us to do so. And you'll be familiar with a series of straight line results. Most of them are associated with the standard formula y equal mx plus c, but we need to look at others, and you need to understand what that means. So that will be in the next screencast.